Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. In practical situations, it is inevitable that a structural section is insufficient in resisting the loads. There is a need to add another different section or complicated composite sections to resist the loads. Since these sections can be broken down into a sum of simpler sections where moment of inertia is already known to you or can be determined by you without difficulty, there is a need to determine the moment of inertia of each simple area with respect to the same axis. So the parallel axis theorem is your guide tool in computing the sum of the moments of inertia of simpler areas with respect to the same axis. So let's have this discussion and let's derive the formula for the parallel for moment of inertia with respect to uh, the same axis. So let's consider this area in general, and we have this differential area here, and we want to determine the moment of inertia of this entire section with respect to this axis AA1 or any axis AA1. And we have also an axis through the centroid of the area or through G, which is axis CC1, so that this differential area is at distance y sub c from the centroidal axis, and the differential area also is at distance y from the axis, any axis AA1. So by definition, moment of inertia with respect to AA1, differential moment of inertia with respect to AA1 is equal to the square of the distance of that differential area, so y square times differential area. And we will call the distance between the parallel axis, the centroidal axis, and this axis here as P, so that differential IAA1 equals y squared dA. Then y is equal to, from the figure, y sub c plus p. So differential IAA1 equals y sub c plus p quantity squared dA. Expanding and integrating, IAA1 equals integral of y sub c squared plus 2y sub c p plus p squared dA. Then expanding, so we have IAA1 equals integral of y sub c squared dA plus 2p integral of y sub c dA plus p squared integral of dA. So take note that p is constant, that's the distance between the parallel axis, and y sub c is variable here. And we then note that integral of y sub c squared dA, so the square of y sub c squared dA is the moment of inertia of the area, expression for the moment of inertia of the area with respect to this centroidal axis or axis CC1, which I'll just call I sub G. And integral of y sub c dA by the first moment of area, this is simply area times y sub G. And p squared integral of dA, the integral of dA, of course, is area. So IAE1 equals, this is I sub G, or the centroidal moment of inertia of area, plus 2p area yg plus p square area. Since yg is 0, that's the value of the distance, or y sub g, which is the centroidal value here, which is 0 because that's the y coordinate of the centroid. So this term, this yg here is 0. Therefore, the moment of inertia with respect to any axis is equal to I sub g, or the centroidal moment of inertia of the area, plus area p square, where P is the distance between the parallel axis, the centroidal axis, and this axis where the moment of inertia is to be transferred to. So I sub AE1 equals I sub G plus area P square. So this is the transfer formula for moment of inertia of area, moment of inertia of plane areas. And that's the actually the proof of this parallel axis theorem. So we now use this transfer formula in verifying the centroidal moment of inertia for common figures which we already discussed in the preceding examples or sample problems just to verify. So for rectangular sections with respect to the centroid, remember that it is bh cubed over 12. Let's check it here. So the centroidal x-axis through the centroid is at distance h over 2. This h over 2 is actually the p here. And assuming we do not know yet the moment of inertia with respect to the centroidal x-axis, and the moment of inertia with respect to the base is bh cubed over 3. So Ix equals I sub gx plus area p square. Ix is bh cubed over 3. Then I sub equals I sub gx plus area of rectangle bh, then h over 2, which is p here, quantity square. So 1/3 minus 1/4 is 1/12. So therefore it verifies that the centroidal moment of inertia of a rectangle parallel to the base is equal to bh cubed over 12. So likewise, with respect to the centroidal y-axis, because this distance is b over 2, so it will result to igy, which is b cubed h over 12. And the polar moment of inertia with respect to the centroid G is equal to igx plus igy, so it is bh over 12 times quantity b square plus h square. So it is just igx plus igy. Then for triangular section, in general, parallel to the base, so let's locate the centroid. Remember, this is h over 3, and h over 3 is the p here. So assuming we do not know yet the centroidal moment of inertia with respect to the centroidal x-axis, and remember it is bh cubed over 36. So let's verify that it is bh cubed over 36. But with respect to the base, it is bh cubed over 12. So ix equals igx for this triangle plus area p square. So bh cubed over 12 equals igx plus 1/2 bh, then times h over 3 quantity square. So 112 minus 1 over 18 is 1 over 36. So that's why the moment of inertia with respect to the centroid of a triangle is bh cubed over 36. And you should be able to memorize this. This centroidal moment of inertia of common shapes, rectangle, triangle, circle, or part of a circle. So for this orientation, on the other hand, so the centroid is h over 3 from the x-axis from the base and b over 3 from the y-axis shown. So igx is bh cubed over 36. igy is b cubed h over 36. So g sub z, or the polar moment of inertia with respect to the centroid g, is bh over 36 times quantity b square plus h square. While with respect to the x-axis, bh cubed over 12, with respect to the y-axis, Iy equals b cubed h over 12. And with respect to the origin, the polar moment of inertia is bh over 12 quantity b square plus h square. For circular section, since the origin is also the centroid of the circle, remember that Ix is equal to Iy by symmetry. In fact, it is also equal to moment of inertia with respect to any diameter. And it is pi r4 over 4. Ix equals Iy equals pi r4 over 4. That's also Igx, Igy, pi r4 over 4. And Jo is pi r4 over 2. So it is simply Ix plus Iy. So again, Ix equals Iy equals Igx equals Igy with respect to the centroid because of symmetry. And this is also Jo or J sub g, the polar moment of inertia. So pi r4 over 2. For semicircle, let's have the centroid. So Ix equals Iy equals pi r4 over 8 or 1 half of pi r4 over 4. So take note that with respect to the x-axis, we have half circle. So it is half of pi r4 over 4. That's why it's pi r4 over 8. Or the other way around, it is moment of inertia of two quarter circles, identical quarter circles. So for a quarter circle with respect to the x-axis, with respect to this axis here, is pi r4 over 16 times 2, so that's why it is pi r4 over 8. With respect to the y-axis, it is the same. It's like quarter circle with respect to say this axis here, which is the same as this. The orientation, you look at the orientation. So that's why Ix equals Iy pi r4 over 8. So it's like two quarter circles, moment of inertia of quarter circles with respect to the diameter or with respect to the radius. Then for JO, it is pi r4 over 4 times 2 of Ix and Iy. Then for the centroid, take note that the centroidal x-axis passes through G, while the centroidal y-axis is also the y-axis. So therefore, Igx is different and Igy is equal to Iy from this case because this is Igy, this is also Iy, so it's the same pi r4 over 8. But Igx is at distance 4r over 3 pi, remember from centroids or distributed forces for locating the centroids of areas. So it is 4r over 3 pi, remember the distance. So that's 4r over 3 pi, and this is the centroidal axis parallel to the x-axis. And the moment of inertia with respect to the x is equal to Igx plus area this p square. So Ix equals Igx plus area p square. Igx is I Igx is also Ix is pi r4 over 8, while area is pi r square over 2. P is this distance 4r over 3 pi. Substitute into this formula, pi r4 over 8 equals Igx plus pi r square over 2, area of semicircle, then 4r over 3 pi, quantity square. So pi over 8, because we have r to the fourth also here, pi over 8, if we simplify this is 16 over 2 or 8 over 9 pi because we can cancel pi. So pi over 8 minus 8 over 9 pi, then times r to the fourth. So Igx therefore is 0.10976 to 5 significant figures r to the fourth. So that is Igx. You may only memorize 0.1098 if you want, but be sure how to arrive with this answer, with this value, so that you can easily remember this also. Or you can de derive this by applying the parallel axis theorem or the transfer formula for moment of inertia. So likewise, IGY, as I said, is IGY is the same IY, so pi r4 over 8. And J JG, therefore, which is IGX plus IGY, so 0.10976 plus pi over 8, that's 0.5025 r to the fourth. You just verify that you just add 0.10976 and pi over 8, then quantity r to the fourth. Then for a quarter circle, this is the centroid, it's the same. XG and YG the same, 4r over 3 pi as shown in the figure. So IX equals IY equals pi r4 over 16 for a quarter circle. Then IGX equals IGY equals half of this value here. So IGX equals IGY equals half of 0.10976, and that's 0.05488 r to the fourth. Or you may use the transfer formula to arrive with this answer to that value. So you have to memorize this also because these sections are common. And lastly, JG is equal to times 2 of this value, so 0.10976 r to the fourth. And lastly, we have an ellipse. So for an ellipse, it's like a circle. With respect to the x-axis, IX equals IGX also, because this is the centroid, and it is equal to pi a b cube over 4. So IX equals IGX equals pi a b cube over 4. And IY equals IGY equals pi a cube b over 4. So for a semi-ellipse, the upper part for the centroidal, you just remember this. So IGX, considering the upper half of the ellipse, so it is 0.10976 a b cube. I just verify that, but it is not common section anymore. But if you want to know the centroidal moment of inertia of the upper or lower semi-ellipse, then it is 0.10976 a b cube. The quantity that is cube is the one that is perpendicular to the axis. And same is true for quarter ellipse and so on and so forth. Then for J O, it is equal to JG also, pi AB over 4 quantity A square plus B square. So that's it for these common shapes or sections. Level 44, determine the moment of inertia of the trapezoidal area about the x and y axis. So here is the given figure. So we will divide this figure into regions into two parts. We have rectangle, and for our solution we have rectangle, this rectangle here with base B1 and height h, and these two identical right triangles with base, this one is b sub 2 over 2 minus b sub 1 over 2, so that would be quantity b2 minus b1 all over 2. So b2 minus b1 all over 2, where the centroid is there at distance 2/3 of h from the x-axis and 1/3 of this part. Now this is 1/3 of this value here, the centroid. So the distance of G from the y-axis would be b1 over 2 plus 1/3 of quantity b2 minus b1 over 2. So this is 2/3 of h, while this is uh, b1 over 2, b1 over 2 up to here plus 1/3 of this value. So b1 over 2 plus 1/3 of quantity b2 minus b1 over 2, which simplifies to, combining like terms, b1 over 3 plus b2 over 6. So Ix is the moment of inertia of a rectangle of base b1 with respect to the base, which is the x-axis. So it is b1 h cubed over 3. So Ix is b1 h cubed over 3 plus 2 times moment of inertia of this triangle with respect to this vertex. If you can recall, times 2. If you can recall, it is base height cube over 4 supposedly, but we'll just use transfer formula here. It is equal to moment of inertia with respect to the centroid. So 2 times moment of inertia with respect to the centroid, which is quantity b2 minus b1 over 2 h cubed over 36. So 2 times IGX of triangle plus area of triangle plus area of triangle times distance between this centroidal axis of triangle and the x-axis, which is 2/3 of h quantity square. But if you can recall, the shortcut is it is equal to 1/4 of this base height cube. So that's the shortcut. But if we apply the parallel axis theorem, so let's just use this. So Ix equals b1 h cubed over 3 plus 2 times quantity b sub 2 minus b sub 1 over 2 h cubed over 36 plus area of triangle 1/2 of quantity b2 minus b1 over 2 times h, then distance is 2/3 h quantity square. So Ix is b1 h cubed over 3, then we have here b sub 2 h cubed over 2 over 36 times 2, so that's b sub 2 h cubed over 36 plus b sub 2, so this is 4 over 9, so cancel 4 times 2, so b sub 2 h cubed over 36 plus 2 over 9 b sub 2 h cubed, so b1 h cubed over 3 plus b sub 2 h cubed over 4. Now this is 1/4 because we have b2 h cubed over 36, 1 over 36 plus this is 1 over 9 b2 h cubed times 2, so plus 2 over 9. So this 1/4 here is 1 over 36 plus 2 over 9. So 1/4 b2 h cubed. Then we have 2 times 1/2, so it's still 1. So negative b1 h cubed over 36 and negative 2 b1 h cubed over 9. So it's also negative 1/4 b1 h cubed. So combining 1/3 and minus 1/4, they are like terms. So Ix is 112 b1 h cubed plus 1/4 b sub 2 h cubed. So factoring out h cubed over 12, then Ix is equal to b1 plus 3 b sub 2 h cubed over 12. So that's Ix. Now with respect to the y-axis, which is the centroidal y-axis also, it is moment of inertia of this rectangle plus 2 times moment of inertia of this triangle with respect to the y-axis. So we used parallel axis theorem here, IGY of the triangle. So 2 times IGY of triangle plus area of triangle distance square. So IY is B1 cube because this is B1. So B1 cube H over 12 with respect to the centroid, take note. So B1
cube h over 12 for this rectangle plus IGY of triangle, which is base B2 minus B1 over 2 quantity cube height over 36. So plus 2 times B2 minus B1 quantity over 2 quantity cube over 36 times H. Then plus area of triangle, which is 1/2 of quantity B2 minus B1 over 2 times H. Then distance is B1 over 3 plus B sub 2 over 6 quantity square. So that's by transfer formula for moment of inertia of areas. So simplifying, this is 1/8, then times 2, so 1/2 divided by 36, 1/4 divided by 36, so 1 over 44 of H quantity B2 minus B1 cube. So let's just have it simplified. So H B1 cube over 12, then plus B2 minus B1 quantity cube over 144. Then let's simplify this part here. This is 2 times 1/2, so 1. So 1/2 of quantity B2 minus B1, H, so over 2 times, this is LCD is 6, divide by 3, so 2B1 plus B sub 2 over 6 quantity square. Then simplifying further and expanding this part, this is B2 cube minus 3B sub 2 square B1, then plus 3B sub 2 B1 square over 144. And if we simplify 3 over 144, that's 1 over 48. So IY is HB1 cube over 12, then plus B sub 2 cube minus 3 B sub 2 square B1 plus 3 B1, B2 B1 square minus B1 cube times H over 144, then plus B sub 2 minus B sub 1 H. Then this one is 4B1 square plus 4B1 B2 plus B sub 2 square expanding over 2 times 36, so 72 in the denominator. So IY equals HB1 cube over 12 plus B2 cube H over 144, or HB2 cube over 144 minus B2 minus HB2 square B1 over 48, 3 over 144, so 1 over 48, then plus HB2 B1 square over 48 minus HB1 cube over 144. So plus 4 over 72 is 1 over 18. So plus B2 B1 square HB2 B1 square over 18, then plus minus B2 B1 square over 18, then plus B B1 plus HB1 B2 square over 18, then plus HB2 cube over 72, then this one minus HB1 cube over 18, then minus HB1 square B2 over 18, and minus HB1 B sub 2 square over 72. So combining like terms, 112 minus 1 over 144 then minus 1 over 18. So that would be hb1 cube over 48, then 1 over 144 plus 1 over 72. So that would be hb2 cube over 48. Then negative 1 over 48 plus 1 over 18 minus 1 over 72. That would be hb1 b2 square over 48. And finally, we have 1 over 48 plus 1 over 18 minus 1 over 18. So this will be left hb2 b1 square over 48, or hb1 square b2 over 48. So factoring out h over 48, then we'll have b1 cube plus b2 plus b1 square b2 plus b1 b2 square plus b2 cube times quantity h over 48. So that's it for this problem. So because it is in terms of the symbols here, that's why the solution is lengthy, but if there are numerical values assigned, then the solution would have been short. Level 45, determine the moment of inertia of the shaded region shown with respect to the centroidal x-axis and establish formulas for n equals 0, n equals 1, and n equals 2. So here's the given figure, and this is the general curve. Remember that we already derived the moment of inertia with respect to the base, with respect to the x-axis, and if you can recall, it is bh cubed over 3 times quantity 3n plus 1. And for the area, it is in general bh over n plus 1, but we will derive it again here. And for the centroid, we will establish formula for the centroid yg. So let's have vertical strip. The height is y, the thickness is dx, and the centroid is, of course, the half, the geometric center of the rectangle. So that distance is x, and therefore this is the centroid of this strip, which is from the y-axis still x, from the x-axis half of y over 2. So that is y over 2. So for our solution, area equals integral of y dx, or differential area is y dx, and y is kx to the n. So when x is b, y is h, so h equals k b to the n. So that means k is h over b to the n. So therefore, the equation of the curve is y equals k, k is h over b to the n times x to the n. So area is equal to h over b to the n, integral from 0 to b of x to the n dx. Of course, integral of x to the n is simply x to the n plus 1 over n plus 1 by power formula. So h over b to the n, quantity x to the n plus 1 over n plus 1 from 0 to b. So if we substitute the upper limit, this is b to the n plus 1. Lower limit would be 0. So the value when substituting the lower limit will be 0. So b to the n plus 1 is the same as b to the n times b. So we can cancel b to the n. So bh, area is bh over n plus 1. So remember, that's the formula in general. So that when n is 0, it is just a rectangle. So the area of rectangle is bh over 1, or simply bh. If n is 1, it is a triangle. The area of triangle is 1 half bh. So this is bh over 1 plus 1. So bh over 2, which is correct. Then if n is 2, it is a spandrel of parabola. So it is bh over 3, and so on and so forth. So by second moment or by the first moment of area, area times yg. So let's locate the centroid, and that's that distance is xg, that distance is yg. By Varignon's theorem, or the first moment of mass, area times yg is the sum of moments of its components, or integral of the moment of this component here, which is y over 2, the moment arm, times differential area y dx. So area yg equals integral of y over 2, the moment arm of this strip from the x-axis, y over 2, times differential area, which is y dx. So area, differential area, moment arm of area, yg from the x-axis, moment arm of the strip. So interpret this as Varignon's theorem, or because you are already in statics, you already experienced this in integral calculus, and I hope that you will not find a hard time interpreting this integral, or this setup integral here. So area is bh over n plus 1 yg equals 1/2 integral of y square, and y square is h over b to the n x to the n, then quantity square dx. So simplifying, yg equals, so this is h square, so we can cancel h, there is h here, n plus 1 times h over 2 b, b to the n, b to the 2n, because we have to square it, b to the 2n times b to the 1 is b to the 2n plus 1. So yg is equal to n plus 1 times h over 2b to the 2n plus 1 integral of x to the 2n dx. Integral of x to the 2n is simply x to the 2n plus 1 over 2n plus 1 by power formula. So yg is quantity n plus 1 h over 2b to the 2n plus 1, then quantity x to the 2n plus 1 over 2n plus 1 from 0 to b. So don't mind the lower limit, because it will just give us the value here 0. When we substitute the upper limit, we have b to the 2n plus 1. And since we have b to the 2n plus 1 here also, we can cancel that. So that means yg is n plus 1 times h over 2 quantity 2n plus 1. So yg equals n plus 1 times h over 2 quantity 2n plus 1. So that's the general formula for the location of the centroid of this region above the x-axis. Then we derive the moment of inertia with respect to the centroidal x-axis by the parallel axis theorem. So that is ix equals ix equals igx plus area yg square. So ix equals igx plus area p square, where p is this yg here, and we already derived yg. Ix is, if you can recall, as I said, from level 4, which we derived the moment of inertia with respect to the x-axis of this region, is, so that's why you have to completely watch the videos from parts 1a, 1b, down to this part, and until it is finished, so that you will have ample of videos, sample videos, and derivation of formulas. And the most important part would be the remembering of the formulas also, especially for common regions. Not this one, because that's not common, but I hope you can also derive formula. You know how to derive the formula. So bh cube over 3 quantity 3n plus 1, that's ix, then equals igx, then area bh over n plus 1, then yg n plus 1 h over 2 quantity 2n plus 1 quantity square. So bh cube over 3 quantity 3n plus 1 equals igx times quantity bh n plus 1 bh cube over 4 quantity 2n plus 1 square. So n, this is n plus 1 square, so there is n plus 1 here, so n plus 1 cancel. Then bh cube over 2 square is 4, then quantity 2n plus 1 square. Factoring out bh cube, so igx equals bh cube, quantity 1 over 3, 3n plus 1 minus quantity n plus 1 over 4, 4n square plus 4n plus 1. If we expand this, then simplifying, this is the LCD, 12 times 3n plus 1, quantity 4n square plus 4n plus 1, or 12 times 3n plus 1, then 2, quantity 2n plus 1 square. Then we have igx equals bh cube 16, this is 16n square plus 16n plus 4, then minus 3 times 3n square, 3n plus n is 4n, then 1 times 1 is 1. So minus 3 times 3n square plus 4n plus 1. That's simply algebra. I hope you can follow that. So igx is 16 minus 9 is 7n square. 16n minus 12n, so plus 4n. 4 minus 3 is 1. So therefore, igx is 7n square plus 4n plus 1 bh cube over 12 quantity 3n plus 1 2n plus 1 square. So that's the general formula. And for n equals 0, so 0, 0, 1, it is moment of inertia of a rectangle, and we know that moment of inertia of a rectangle with respect to the centroid parallel to the x-axis is bh cube over 12. So this should give us bh cube over 12 also when n is 0. So when n is 0, the numerator is simply 1 bh cube, so bh cube. Then this is 1. This is also 2 times 0 plus 1. 1 square is 1, so over 12. So it's correct when for n is 0, igx is bh cube over 12. When n is 1, this is a triangle, and the moment of inertia of a triangle with respect to the centroidal axis is bh cube over 36. So 7 times 1 square is 7, plus 4 times 1, 11, plus 1, 12. Divide by 12, so cancel 12, bh cube. So this is 3 times 1 plus 1, so 4. 2 times 1 plus 1, 3. 3 square is 9. 9 times 4 is 36. So it's really correct that when n is 1, igx for a triangle is bh cube over 36. And finally, for n is 2, 7 times 2 square is 28, plus 4 times 2, 8, so 36, plus 1, 37. 37 bh cube over 12, quantity 3 times 2 plus 1, this is 7. 2 times 2 plus 1 is 5. 5 square is 25. 25 times 12, 300. 300 times 7, 2100. Therefore, igx is 37 bh cube over 2100 for n is 2. So that's it. You may not familiar with this, you may not memorize this, but you should be able to derive this. And we have checked that for n is 0, rectangle, that's correct. For n is 1, triangle, that's the moment of inertia with respect to the centroidal x-axis parallel to the base of a triangle. And for n is 2, 37 bh cube over 2100. Level 46, determine the moment of inertia of the shaded region shown with respect to the centroidal y-axis, and establish formulas for n equals 0, n equals 1, and n equals 2. So here is the given figure. This is the same as in level 45 problem. This time, let's derive the centroidal moment of inertia with respect to the y-axis. So we already know the area from the preceding problem, level 45, that it is bh over n plus 1. So this is the strip considered. Height is y, thickness dx. So the centroid is at distance x from the y-axis and y over 2 from the x-axis, which is already discussed in level 45. And the centroid is here. The distance is xg from the y-axis and from the x-axis yg. But we need to derive xg. So area times xg equals integral of x dA, and dA, x is the moment arm of the strip from the y-axis, and dA is simply area of the strip, which is y times dx, differential area. So we already know that y is h over b to the n, k is h over b to the n, then this is x to the n. So bh over n plus 1 times xg equals integral from 0 to b of x, h over b to the n, x to the n dx. And h over b to the n is the value of k from level 45. So simplifying, xg is n plus 1 over, we can cancel h, over b to the n plus 1 because there is b here. Then integral of x to the n plus 1 dx. So x equals n plus 1 over b to the n plus 1, integral from 0 to b of x to the n plus 1 dx. Of course, integral of x to the n plus 1 is x to the n plus 2 over n plus 2. So n plus 1 over b to the n plus 1, quantity x to the n plus 2 over n plus 2 from 0 to b. So xg is n plus 1 over n plus 2. Then this is b to the n plus 2, which is b to the n plus 1 times b. So we can cancel b to the n plus 1. So there remains b here. Don't mind the lower limit, 0. So therefore, xg is n plus 1, quantity n plus 1 over n plus 2 times b. So iy equals igy plus area p square by transfer formula. So b cubed h over 3 plus 1. By the way, iy, which we established in level 4, this is the moment of inertia with respect to the y-axis of this region in general. B cubed h over 3 plus n equals igy. This is the area. Then distance, which is n plus 1 over n plus 2 b quantity square. So igy equals, factor out b cubed h, so 1 over 3 plus n minus uh, n plus 1 over n plus 2 quantity square. This one after we simplify this, times b cubed h. So igy equals n square plus 4n plus 4 minus quantity 3n plus n, so 4n, n times n square, then 3 times 1, 3. So minus quantity 4n plus n square plus 3. Then b cubed h over n plus 3, quantity n plus 2 square, the LCD. So n square cancelled, then 4n minus 4n cancelled, 4 minus 3. So therefore, the numerator is b cubed h, the denominator is n plus 3, quantity n plus 2 square. So that's igy, b cubed h over quantity n plus 3, n plus 2, quantity square. So for n equals 0, it is a rectangle, so we expect b cubed h over 12. So this is 0, 3, 0, 2 square is 4, 3 times 4, 12. So that's why it's b cubed h over 12, really. When n is 1, triangle with respect to the y-axis through the vertex, it is b cubed h over 4. So when n is 1, this is 4. b cubed h over 36 rather, uh, because it is with respect to the centroidal y-axis. So this is 4, this is 1 plus 2, 3, 3 square 9, so 4 times 9, 36. So it's really b cubed h over 36 for n is 1. And for n is 2, this is 4 square 16, 5, so 80. So for n is 2, IGY is b cube h over 80. So that's it. This is xg. So that's it. B cube h over 80.